Hello, welcome back for the last chapter. We are going to look at chapter 10. It is all about correlation and regression. So I know in earlier algebra classes, you have learned about linear equations. And we're going to kind of tie in some of that knowledge with what we've learned about statistics this semester. So we're going to learn how to create a scatter plot of data. We're going to learn how to compute the correlation coefficient. We're going to test the hypothesis today on two variables and how they're related. We're going to compute the equation of the regression line, and we're going to compute the coefficient of determination. And we probably won't get to this, but it's one thing that would be good to learn is computing the standard error of the estimate. Let's just cross that off. Okay, so scatter plots and correlations. Sometimes the researcher has reason to believe that two or more variables are related. One variable would be called the independent variable, a variable in correlation and regression analysis that can be controlled or manipulated. The dependent variable, a variable in correlation and regression analysis that cannot be controlled or manipulated. The value of the dependent variable usually depends on the value of the independent variable. So for example, decide which variable is the dependent and independent variable in each of these scenarios. So I'd like for you to take a minute to look through them and for you to decide. Pause the recording and then come back. Okay, now that you've had a minute to look these over, it says for a random selection of drivers, their ages and the number of automobile accidents that they had over a 3-year period are shown. So for the independent variable, it would be the thing that we could manipulate or change would be their age. And we think that the age of the driver probably has some indication on the number of automobile accidents. So number of accidents would be dependent. Okay, letter B. Blood levels of sodium in milliliters equaling liters. I'm not sure how that's read. And the systolic blood pressure. So your sodium level versus your systolic blood pressure. So the thing that could be changed or manipulated would be your sodium intake. Your sodium level in the blood. And we're thinking that that affects your systolic blood pressure. So the dependent variable would be your systolic blood pressure. The number of students in a class and the average grade per student. So the individual or the independent variable would be the number of students in class. And the dependent would be the average grade per student. I'm not saying that there's for sure a relationship between each of these groups of variables, but that's how we would pick out the independent and dependent variables. Okay. So once we have two variables that we would like to check out and see if there's a relationship between them, the first observational visual way that we can look at this possible relationship is using a scattergram or called a scatter plot, a graphic tool used to display the relationship between two quantitative variables. The explanatory variable is on the x-axis and the response variable is on the y. So let's tell us something about correlation visually. Scatter plots only give us a visual way to give us an objective way to look at the potential relationship between two variables. Statisticians use a measure called the correlation coefficient to determine the strength of the linear relationship between two variables. So that's going to be our numerical. The correlation coefficient is going to be our numerical objective way to decide if there's a relationship. So just looking visually here, these are 4 sets of scatter plots that we could see. This top left here is a positive linear relationship. Now, remember, when we learned about linear equations back in your algebra class, you probably learned about an exact equation of a line. And in real life, variables don't always happen in an exact equation of a line. They will appear approximately linear. This would be a positive approximate linear relationship. This would be approximately a negative linear relationship, but they're not always perfect. And then the one down here is a curvilinear relationship. If you remember back to your algebra days, that would be called a quadratic equation here. And then this one over here is there's no relationship. You can't really put any positive or negative to it at all. Okay. So the way that we are going to find the correlation coefficient is by typing into Desmos this equation here. So we're going to have a table of data that is going to be the independent variable in X1 and the dependent variable in Y1. And then we're going to type this into Desmos. It's going to reference X1 and Y1 to create a linear, because we're putting it in the format of a Y equals mx plus b, where m is the slope and b is the y-intercept. Now, we're not going to spend a lot of time in this class going through the slope and intercept and what they mean and everything, but we're basically just going to use a scatter plot for a visual look, and then we're going to use this equation modeling. So this is modeling, it's what's called a regression equation, a linear regression equation. And this R is our correlation coefficient, and that tells us how well the data fits a linear model. So, and this is not any data right here. This is just an example of how we're typing it into Desmos. So this R here is a negative 0.67. The negative tells us it's a negative relationship, and the 0.67 is going to be on this scale here. And so we're going to dive more into the scaling later. Back in your notes. Is where it tells us that you can draw it right on here, actually. A negative 0.8 to a negative 1 and a 0.8 to a 1 is going to be a strong relationship. And then we've got a negative 0.5 is going to be a moderate negative. And a moderate positive. And then negative 0.3 to negative 0.5 is a weak negative and a weak positive relationship. And then from negative 0.3 to 0.3, there's no relationship. So this little example here that I have in the notes, a negative 0.67 would be in this moderate negative relationship. Okay, so we're going to get practice on our own. We're going to look at these in Desmos. I do not expect you at this point to look at these in ALEKS. There may be assignments later on in future semesters, but this current here. So depending on what video you're seeing, you may have ALEKS assignments, but currently there are not. I'm having you just look at them in Desmos so that you can complete them in Canvas. So we're going to go to Desmos, and for each of these, you can see every time I give you a table, I'm expecting you to make a table in Desmos so that we can see their scatter plot. So that'll kind of get you started. So go ahead and open up your Desmos, and I'm going to do that as well. And here is my first set of data. It is the table that has the age of drivers and the number of accidents that they have been in. And mine are an X2, Y2. Yours might be an X1, Y1. That's okay. We just have to make sure we refer to the appropriate columns when we go to do our modeling. So when you do this, you will probably have to hit your little magnifying glass on the left. I've already done that, so I don't have it, but it'll be down here in the bottom left where my mouse is. And that will give you the scatter plot. And then you're going to go down here and type what I've highlighted here. Now, depending on what your columns are, you might have Y1. This tilde symbol right here is found to the left of your 1 key on your keyboard. And then you're going to type M, just the letter M, and then X2 plus B. And then you can see down below, it's going to give you M. It's going to tell you the slope that's appropriate for this data, and it's going to tell you the B. Just make sure your numbers match mine. Again, we're not going into the slope and the y-intercept and what they mean in this lesson, but I just want to make sure your numbers match. So most importantly, you want to make sure that your R matches my R. So you should have an R of a negative 0.9234. Okay, so if we go back to our paper, then we should see that that's our correlation coefficient, and it tells us that there is a strong negative relationship between the two variables, which means as the age of a person increases as they get older, they're going to have fewer accidents. Okay, we're going to do the same thing here with example 3. So let's go ahead to Desmos. We're going to enter in the sodium level in the X and the blood pressure in the Y. And then we're going to type your command in Desmos. Get to that here. I'm going to close that one up. And then here's the blood pressure one. So I've added, and then I have to go up and turn off those pictures. I'm just going to click on those pictures to turn them off. And then I'm going to turn these on. And now I have to hit the magnifying glass to get my data to show up. And it rescales it, which is so nice. And you can see that there's definitely a positive relationship here. And my columns happen to be X4 and Y4. Yours maybe something else. Just make sure you refer to them appropriately when you type in the Y4 tilde MX4 plus B. And what you really want to make sure is that you're getting the same R that I'm getting here, because you're going to have a homework assignment and a quiz in Canvas that you'll need to be able to complete these for. So let's go ahead and write this on our paper. The correlation coefficient is 0.9394, which is a strong positive relationship. Okay. So next up, we want, because we've been doing hypothesis testing this semester, we want to have a way to see, how do we know if it's a really good fit or not, right? How can we run a hypothesis test? And there actually is enough relationship here to say that there's a linear relationship. So the formula for the t-test, so you're going to get a t-score just like we did and we used in ALEKS, but we're just going to do all of this by hand. is the correlation coefficient times the square root of n minus 2, n is your sample size, the number of pairs of data that you have, and then 1 minus that r squared. And let's just dive into one. So we have data here that says school administrators wonder whether class size and grade achievement were related. A random sample of classes revealed the following data. Are the values linear related? Draw the scatter plot, compute the value of the correlation coefficient, okay, state the hypotheses, test the significance of the correlation coefficient at alpha 0.05, and give a brief explanation of the type of relationship. Assume all assumptions have been met. Okay. So first thing we're going to do is we're going to go to Desmos and put in our data. I'm going to turn these off for just a moment. And there we go, and get a scatter plot. Okay, so here is that grade data. I like you to take a minute to put yours in. Make sure that you're getting the same R that I am getting here. And also the same test statistic that I'm getting, a negative 1.82. Okay, so now that you have verified my numbers there, we are going to see how we can prove this hypothesis statement. So let's go back to our paper. And we are going to now state the hypothesis. So the hypothesis is that this is called, this little p here is called a row in Greek letters. So we're saying that the relationship is equal to 0. And then the alternative is that this row is not equal to 0. Okay. Now there's a couple ways that you can reject this and say that there is a relationship. So one of them is by taking the correlation coefficient and computing your t. So when I do that, I took all my data here, and on the next page, you'll see that we found our t. So it's a negative 1.82. So we need to find our critical t values. So this is finding our critical t values. It's using the table A8. I scan this page in, and you can print out this page if you want, just so you've got it handy for yourself. But this is what page A8 looks like. Now, remember when we're doing this regression hypotheses, we use n minus 2 as our degrees of freedom. So for this problem, we would have 6 minus 2 or 4. And so for an alpha at 0.05, our critical value is 0.811 plus or minus. Okay, so our danger zone is a negative 0.811 or positive 0.811. So this is danger zone, danger zone. Okay, and then our test statistic is this. So this is our test statistic. So we are at a negative. So our test statistic falls here. We're past that. So because the test statistic and negative 1.82 is less than the negative 0.811, we reject H0. So I think I maybe mistyped this here. I misspoke. I misspoke. So our this is not our critical value. So if we want to use just our hour, so this is not a critical value, our critical T values are on A5 on page 799. And so we would be looking at 0.025 comma 4. So our critical value, sorry about that, is at 0.025 and 4, so 2.776. So our test statistic is not, it's a negative 2.776 and a positive 2.776, and we are not it's greater than our test statistic. So we do not reject. Okay, we're not in the danger zone. So let me redraw the picture here. I apologize. I misspoke because there's two ways that you can reject this. So our test statistic is, this is the danger, is a negative 2.776 or a positive 2.776. This is danger here. And our test statistic, the negative 1.82, is really right here. Okay, so that's using the test statistic. Now you can also just use, you can also just compare the absolute value of R, which is the absolute value of a negative 0.6731, which is comes out to be 0.6731. And if that is, it's just like the kind of like the p-value. So this table A8 is like a p-value table for regression. Okay, so that's where we went to the table A8, pardon me, at 0.05 and 4. And so our p-value is 0.811 that we're looking at. So if R if that row or the R, the correlation coefficient, is greater than the critical p-value, then reject H0. If R is less than critical p-value, then do not reject. Okay, and so because our absolute value of our R is the absolute value of R, so our absolute value of R is less than the critical p-value from the table A8. And so this matches using the test statistic. We're going to do another one so that I get it straight. Let's look at example 5. So example 5 is the data from example 3 on the blood levels of sodium versus the systolic blood pressure. And we already said that we had a relationship here. And so let's go to our Desmos so we can just check it out. I'm going to turn off these graphs. Let's just look at the data from the blood pressure. Let's go back up and open those back up here. So we said there is a relationship. And our R's correlation coefficient was 0.9394, so it was high. So I'm calculating the test statistic. The test statistic is probably the easiest way, just because when it's really large, you can already tell you're going to reject. It's 6 standard deviations away. It's very rejectable. We can also compare the 0.9394 to the table A8. So let's do both ways. So I am just going to show you on paper the test statistic. Method. Versus the table A8. Okay, so let's go back to our paper. So we've got all this written down here. So our hypothesis test is that the R is equal to 0, the correlation, there's no relationship. And HA, the alternative, is that it does not equal 0 and that there is a relationship. So our test statistic is taken R here, the number of pairs was 7 minus 2, and then 1 minus R squared, and that comes out to be 6.13. And then the critical T value is going to be the T of 0.025 and 7 minus 2 or 5. And so that's from table A5. We're going to use this critical value. So table A5 at 0.025 and degrees of freedom of 5 is 2.571. Plus or minus, because it's two-tailed. Point two-tailed. Alpha is 0.05 and it's two tails. So we're going here, it's 2.571. Okay, so we have critical danger area is anything out here. So smaller than a negative 2.571 or bigger than a positive 2.571. And this is us. We're way out here. So very dangerous. So we reject H0. Okay. Or we can say the absolute value of R, which is the absolute value of 0.9394 is 0.9394. And then we want to compare that to the p-value, critical value on table 8. at 5. So at 5 and 0.05 would be 0.754. It's greater, so 0.754. And so because the absolute value of the R is bigger, 0.9394 is bigger than this critical p-value, we reject. So both of these things tell us that we're going to reject. And then the conclusion is there is sufficient evidence to support the claim that there is a linear relationship. Okay. And then the last few pages of this lesson are just showing you some characteristics about correlation coefficient, things that we've already talked about, positive and negative, and the rules of thumb that we're going to use. That's me that for video lesson for 10.2.